Welcome to this class. So today I am discussing about the total number of spectral line. How do we calculate it? So to know what are the spectral lines? So these are the just like that. If this is 1, if we want to know how many spectral line are present in between 4 and 1, n is equal to 4 and 2 is equal to 4 and n1 is equal to 1, then we need to calculate how many lines can be between these. So let's make it 2 lines here, and to get from 4 to 1 we can come directly from here to here, or we can come from here to here and then here to here. This is another. And if we want to come all the way from 1 and then here and then here, so these are some of the process in which the electron come from all the way from top to the bottom in spectral lines. So how many possible spectral line can be formed? So this is 1, this is 2, this is 3, and this is 4, and this is 5, and 1 is from here to here and directly from here to here. So this will be 6. So there are 6 possible transitions that can be possible in this spectral line form. So how many can be formed if we get a little bit of more spectral lines? So we cannot do all this calculation, all these combinations ourselves. So to get this easily, we got a formula of calculating that number of spectral lines is equal to n2 minus n1 n2 minus n1 plus 1 upon 2. So this is a formula for calculating the total number of lines. So let's put this n1 and n2 value here with 4 and 1. If we put n2 4 minus 1 and n2 4 minus 1 plus 1 upon 2, so this will be 4 minus 1, 4 upon 2. So this will be 3 into 4 upon 2. So this will be 12 upon 6, and 6 will be the spectral lines which is possible. Now let's get back to another topic, which is effective nuclear charge. So this is basically it is arise due to the repulsion of inner electrons. So what are inner electrons? Just like that, a shell is present, and this is an electron here, these are 2 electrons here, and these are 6 electrons here. So these are called inner electrons, these are called inner electrons, and this is an outer electron, and this is a nucleus. So the attraction of nucleus to outer electron is affected by the presence of these inner electron orbitals. So there are 2 types of attraction and repulsion has been seen in between these. So attraction by nucleus, nuclear attraction, and the second one is repulsion by inner electrons. So these are inner electrons, their repulsion causes the Z effective, the effective nuclear charge, to decrease. So there is a definition for effective nuclear charge, as you can see, according to which due to repulsion of inner electrons, the nuclear attraction for outermost electron decreases, and this decreased nuclear charge is known as effective nuclear charge, and this is explained with the help of Slater rule. So what is Slater rule? Slater is a scientist who discovered a rule. It gives information about the Z effective, the effective nuclear charge, according to which the Z minus sigma, it is the formula for Slater rule, and this Z is the atomic number, and the sigma is the Slater constant. And for calculating the value of sigma, we use some method. So this is the formula for calculation of sigma. And if in an electronic configuration, let's take an example of sodium. It has 11, so the electronic configuration is 1s2, 2s2, 2p6, and 3s1. So we need this is called the last shell. It is n shell, last shell, and this is called n-1 shell, and this is called the remaining electron. This is described in the form of subshells. The shell in which the electron is filled. This is so this is the formula, which is only applicable when the last electron present in s and p orbital, and it is not applicable for d and f orbitals. Okay, so for calculating the sigma, a Slater constant, we use 0.35 into number of electron present in n shell plus 0.85 into number of electron present in n-1 shell plus 1 into remaining electrons. So according to this formula, let's put the values. So what are the 0.35 for calculating sigma? 0.35 into how many electrons are present. So we are calculating the number of we are calculating the 1s orbital. So here 1s is present, so we cannot put the value 1 here. We put the value 0 because it is calculating. This is the orbital in which we are going. So the n value is 0 plus 0.85 into the n-1 shell, which is this, and this shell, the total number of electron here is 6 plus 2, 8, plus 1 into 2 is 2 because 2 is the remaining electron, and here 1 into remaining electron is present. So if you calculate this, we will get 0 plus 6.8 plus 2, and the sigma value come here is 8.8. So this is not the Z effective or effective nuclear charge. So to get the effective nuclear charge, Z effective, we use Z minus sigma. Z is the atomic number of sodium, which is 11, minus 8.8. So the final Z effective value for the 3s electron is 2.2. So now let's discuss when the last electron present in D and F shell. If the last electron in the electron configuration present in the D and F shell, then what will be the formula? So for calculating the Slater constant, we use 0.35 into number of electron present in D subshell. So this is the number of electron present in D subshell plus 1 into remaining electron. This is the formula for calculating sigma in D and F subshell. So let's take an example here, Zn30. So we need to find the 3D. If we are Z effective nuclear charge on 3D orbital, then we use electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, and 3d10. Why 3d10? Because here this is come in first subcell, this is come 8 electrons, and these are the 18 electrons. So this is the final value. 4s is not calculating. So the sigma value is 0.35 according to formula into 9. What is 9? 9 is the number of electron present in D orbital. Means number of electron present in D orbital means this. There are 10 electron. So 10 minus 1. 9 electron will remaining. We were calculating 1, so 9 is multiplied plus 1 into remaining electron. How many remaining are there? 6 plus 2 plus 6 plus 2 plus 0. These are all the remaining electron here. So after calculating we get 21.1.15. So Z effective nuclear charge for 3D orbital is 30 minus 20.5, then 8.85 will be the answer. There are one more key concept for that. If you want to calculate effective nuclear charge on the periphery, so for calculating that we count all the electrons present in it, the molecule. Just like we cannot, if anything ask about the, just like Na11, then we will be using all the electrons present. We cannot ignore the one electron that we used to do in our previous explanation. And another application or the note that we can get from here is the Z effective charge on 1s orbital. So this is important. For 1s orbital, the sigma value that we used to take 0.35 is into 1, or 0.35 will be the answer. So this is not correct. This is not the actual way to answer this. So we use sigma value for 1s orbital is 0.30, not the 35, 30 into 1, so it will be 0.30, and this will be the effective nuclear charge for 1s orbital. Now let's discuss about the modern periodic table. So as we all know, we are discussing periodicity. The periodic table is important here. So what is a periodic table? Periodic table is the arrangement of different elements present in nature. So we arrange that in modern periodic table just like that. An S block is present here. There are rows and columns basically. So there are this first row from hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. This is the first row. This is the first column, and this is second, the beryllium family, and this is another column. If we go down the group, this is called columns, and these are the rows. So there are basically 18 rows are present and different columns. So these are divided into 4 blocks. First is S block element. This is S block element. First column and second column come under this. After that, P block element as P block element. Here 13, from 13, column number 13 to 18, and D block element, which are in the middle of the periodic table. And these are also called transition element. These are also called transition element, and these are called alkali metals, and these are called alkali earth metals. And there are F block elements as well, which are called lanthanite and actinides. This come from here and here. There are 14 elements in F and 14 elements in these. So now let's discuss about what is atomic radii. So atomic radii is nothing but the distance between nucleus and the outermost electron. So we know that that if the number of shells increases, if we go down the group, then the size of the element is also increases, and if we go across the period, then the number of electron is increasing, so size of the element is decreasing, and also the Z effective charge is increasing, so the size is decreasing. So there are some basic trends in periodic table and some of the exceptions which are also present. So let's talk about the group 1. As we know that if we go down the group, just like lithium, as we know, if we the myth is that if we go down the group, the size is increasing. This is the basic knowledge. But what happened here is due to presence of F subshell, and the poor shielding of that, due to presence of F subshell, poor shielding is happening there, and due to which Z effective nuclear charge जो रहता है बढ़ जाता है and size decrease. So the trend is Li ne ke rev says fr. This is not an actual size comparison. So the basic size comparison is Li ne ke rev fr then cs. So this is an actual trend that we see in group first. So this is the basic change that is seen here, and this is same applicable for group 2 as well. We know that B L V till this B as we know, down the group size increases, but here there is exception in which RA will go here and BA will go here if we compare size. Same reason will be applied here. Due to presence of F subshell, poor shielding, Z effective charge increases and size decreases. Now let's talk about the group 3 to group 12, which is the D block element. So here a 3D group is present, a 4D and a 5D period. So we know that if we go down the group, the size is increasing due to addition of more electron in the electronic number. So size differences can be seen here is cesium is greater than Y and greater than La. But after that, here Ti, Zr and Zf. Why is that happening? Because of the presence of lanthanoid group, due to which F block element 14 group are present. So F subshell, due to poor shielding, the effective charge increases, size decreases. These are the same reason which is applicable, and we can speak that Zr and Nb and Mo and W tungsten and Tc and Re will have the comparable size. So there is one question, which of these molecules will show comparable size? So Zr and Hf, which are Zr and Hf, will show comparable size. So there is one exception in group 13. Here B, L, Ga and till. Here in Ga, a D subcell, in D subcell Ga, decontraction due to presence of decontraction. This is due to presence of decontraction in Ga. The size difference will be like this. So this will be the actual order in which, and this Ga and this is the change where we see this